Thanks, everyone. My name is Chris Armstrong. I'm the Deputy Vice-Chancellor Research at the University of New England. I'd like to begin this evening's procedures by acknowledging country. We're here in Armidale, which is Anaiwan land, and I'd like to particularly pay respects to the Anaiwan people and also the other nations around this area who have a cultural affiliation with this space, including the Gumbaynggirr people, the Kamilaroi people, the Dunghutti people, and other countries and cultures as well. I'd like to pay respects to elders past and present and recognise the strength and resilience and capacity of the Aboriginal community. I'd firstly like to just acknowledge that we're here today with a particular focus on the fantastic Professor Yihong Du, who's recently been awarded a Laureate Fellowship, Australian Research Council Laureate Fellowship, which is the most prestigious fellowship you can get in Australian research. So we're here to hear a presentation from him today. This is a partnership, this event, between the Royal Society of New South Wales and the University of New England. We've been undertaking some exciting activities recently with the Royal Society of New South Wales, and so I'm really pleased to have here today Dr. Susan Pond, who's the President of the Royal Society of New South Wales. And I might hand over to her, who's going to say, Susan will say a few words.
Thank you, Chris. I'll get started. I'm most honoured to be speaking to you this afternoon. Excuse my raspy voice. As President, as Chris said, of the Royal Society of New South Wales, and to participate in this joint meeting with the University of New England. In 2021-22, the Society celebrated 200 years since its early days as the colony's first learned society in 1821, which was led by the then Governor and astronomer Sir Thomas Brisbane as its honorary president. Throughout its history, the unique value of the Society has been its dedication to fostering public interdisciplinary exploration of the whole gamut of the human intellect and complex challenges of the day. The Society conducts its work through meetings, symposia, publications, awards, its precious collection of books and archives, and engagement with other national and international organisations dedicated to the power of knowledge. Since its inception, the Society has enjoyed vice-regal patronage, and many of you will know our current patron, Her Excellency the Honourable Margaret Beazley, ACKC, Governor of New South Wales. The Governor, jointly with the Society, convenes Ideas at the House, a series of lectures in partnership with the Society at Government House that are dedicated to the exploration of important and influential ideas. Her Excellency also hosts the annual day-long forum that we hold in partnership with Australia's National Learned Academies. And if you're interested, the theme for this year on the 14th of November is one of the major challenges of the day, threats to democracy. All of these events are held in person and also live streamed from Government House. The Royal Society of New South Wales today consists of 700 members, 450 of whom are fellows and 250 of whom are members or associate members. We recognise special achievements through our distinguished fellowship membership category, and acclaimed Shakespearean actor and director John Bell, AOBE, is our most recent distinguished fellow, appointed last month. Importantly, we are the Royal Society of New South Wales, with branches in Western New South Wales, the Hunter region, the Southern Highlands, and as endorsed at our council meeting last week, the New England Northwest region. Each branch has its own vibrant economic, scientific, industrial, agricultural, civic, and artistic communities. In the case of New England Northwest, it is, of course, very well served by its strong education sector. As it happens, the Society is not new to New England. Geologist Professor Richard Stanton AO, who joined the Royal Society in 1949, was one of its longest-standing members. During his career, he received several awards from the Society, including the Ollie Prize in 1972, the Society's Medal in 1973, and the Clark Medal in 1998. He presented the Clark Memorial Lecture in 1985. Richard Stanton was made an inaugural Fellow of the Society in 2009 and elevated to Distinguished Fellowship in 2012. He was also instrumental in the successful operation and served as a long-standing chair of the New England branch of the Society. His obituary is published in the Society's Journal and Proceedings in 2020. Regrettably, the New England branch fell away when Stanton retired from the University of New England in 1986 and moved to Canberra. But not before March that year, when he was part of the ceremony at the university held in conjunction with the 25th anniversary of the New England branch of the Society. The ceremony marked the presentation of the entire collection of the Society's Journal and Proceedings since it was first published in 1822 to the then Chancellor of the University of New England, Robert Robertson Cunningham. This collection is held in the Royal Society of New South Wales room in the Dixon Library. All issues of the journal published since then are available for open access on the library's main shelves. So we have a long history with the New England Northwest region. Most recently, on the 30th of October last year, I was delighted to join Lou Conway and the Smart Region Incubator in this room, very room, in the evening for a presentation and all day touring solar farms and other points of interest in the Armidale region for the day-long exploration of Clean Tech Futures 2023, electrification and opportunities for community and business. This was held in partnership with the Society. So on that note, I'm very pleased to hand back to Chris Armstrong, Deputy Vice-Chancellor of Research of the University of New England, to tell you about the re-establishment of the New England Northwest branch of the Society and to introduce tonight's speaker. Thank you, Chris.
Thank you, Susan. And thank you for all your efforts as president, and I really love working with you over the last period, including on that event last year. I think that was a fantastic event. It drew a lot of people, a lot of interest, and a really exciting panel session. So thank you for your assistance and participation with that, and also to Lou Conway, who is the director here. So I would like to welcome you to the Smart Regions Incubator. The incubator is a partnership between the University of New England and the Armidale Regional Council. It used to be the library. Yihong was saying when I walked in that he remembers it as the local library, but it's a really fantastic renovation and a really vibrant place for people to come and incubate new companies and build collaborations with community and the university. I'd like to particularly welcome those online as well, and hope that everyone has a really enjoyable event tonight and gets a lot out of listening to Yihong. I'd like to point out that the university, we're in our 70th anniversary year this year, so it's great to be able to launch this new, well, not that this is the launch, Susan, but to start talking about this new collaboration. And it's 70 years since we became a standalone university. We have a strong track record in research and teaching at UNE, and we have great impact. And as Susan mentioned, it's important that we think about how we can think about multidisciplinary activities, multidisciplinary research, and we also bring in the teaching as well. We've got real strengths at UNE in history and humanities, nursing and rural health, agriculture, livestock, soil sciences, environment and biodiversity, genetics, law and regulatory science, and of course, mathematics. Thanks in no small part to Yihong and his team and collaborators in pure mathematics at university. We're working to build collaborations at UNE and to build collaborations that are really strong. And those collaborations are not only internal, but also externally with industry, local government, state governments, federal government, and of course with learned societies, and in particular the Royal Society of New South Wales. I'd like to just take a moment to really acknowledge the work, the tremendous work that Professor Trevor Brown, Emeritus Professor Trevor Brown, did to develop the proposal, and working particularly with Professor Derek Baker, both from University of New England. They put in a phenomenal amount of work, really dedicated effort, bringing together people to kind of develop what a new branch could look like, or a new reformed Royal Society of New South Wales branch in the New England Northwest region. As Susan mentioned, the council approved the formation of the branch at its meeting on the 21st of August. So we're really excited to be getting into planning the launch, the official launch, at an event later on this year. And we're really hoping that the patron, Her Excellency the Governor, will be able to attend, hopefully, but also very much hopefully the President as well, Susan. So from 2025, we're planning that the branch will host at least 2 events each year, and these will be formatted to really highlight the region's expertise and experience and heritage. But also it will facilitate communications and contribute to public debate and policy, foster networking within and beyond the region. The branch will encourage nominations for the Society's prestigious awards, and from those people in the region with outstanding achievements. I'd like to really point out that for this year, the closing dates for the awards are the 30th of September, so the end of this month. And the awards, there's a number of categories of awards that the Royal Society offers. There's an award for Aboriginal and Torres Strait Islander Scholars Medal, James Cook Medal for Lifetime Career Contributions, Edgeworth David Medal for Mid-Career Researchers, Ida Brown Early Career Medal. And the Royal Society also provides a set of alternating sets of discipline awards. This year there's the Pollock Award and Lectureship in Physical Sciences and Mathematics, the Poggendorf Award and Lectureship in Agricultural Science and Environmental Science, and the Award for Humanities, Philosophy and Law, and the Milner Interdisciplinary Award, as well as Early Career Researcher and Student Awards for postgraduates, early career researchers, and postgraduate Jack Kelly Awards. So there's a lot of opportunity there for people in this region to put in bids or put in applications to be award winners. They're very prestigious. Now, the main event, one of the parts of the main event is to introduce Professor Yihong Du. Professor Du has been a Clarivate Web of Science highly cited researcher in 2018, 2019 and 2020, and a Fellow of the Australian Academy of Science from 2021. And as mentioned before, he was awarded an Australian Laureate Fellow this year. So the title of Professor Du's talk tonight will be Mathematics for Propagation and Spreading of Species. So propagation is a phenomena observed in real world with different forms. For example, it occurs in ecological invasion, where an invading species is expanding into a territory, or it can happen when an epidemic, such as a disease, is spreading to new areas. Professor Du and his team use mathematics and a particular class of partial differential equation models to really try and successfully reveal some key features of propagation. I'm really looking forward to Professor Du's talk tonight. He will provide some of the history of his work in propagation and also some new developments on the mathematics of modelling of propagation. Professor Du has quite a long CV. He obtained his PhD in 1988 from Shandong University in China. He spent 2 years at Shandong University as a lecturer and 1 year at Heriot-Watt University in the UK as a visiting fellow. And then in 1991, he joined the University of New England as a postdoctoral researcher, working with Professor Ian Dancer on an ARC project. The then Dr. Du became a lecturer at UNE in 1993 and was then promoted to professor in 2008. Some of his recent work has looked at the investigations in mathematical models for propagation, as I mentioned, over a spatial domain with a moving boundary. And it was for this research that he achieved, it was for this and other research that he achieved the distinction of being elected as a Fellow of the Australian Academy of Science and awarded the Australian Laureate Fellowship in the ARC. So I'm going to hand over to Professor Du and look forward to your talk tonight. Thank you.
Thanks, Chris, for your kind words, and thanks, Trevor, and other organizers for making this happen. I'm really glad here. And as I mentioned to Chris, this used to be the town library. I remember this fondly, this place. I was a very frequent visitor here when the kids were young, and my wife doing shopping on Saturday morning, so I would take the kids here, enjoy the whole morning. Yeah. And today I'll talk about mathematics. However, and you will see some formulas. However, the talk does not depend. It's not based on any understanding of any of the formulas appearing here or later. So I will try to explain some of our findings through some videos obtained from numerical simulation. And first, let me start by introducing some examples in invasive species. The first one is the spreading of a muskrat in Europe. So we will say this a little later with more details. And the second one is these notorious sugarcane toads in Australia. And they were introduced in 1935 with the hope of controlling insects, bugs in a sugarcane field in northern Queensland. But as a result, actually, they turned out to be an invasive pest, and we still have no control of them. And recently, they were already found near Sydney. So no control yet. Now the question is that, how can mathematics help? And there are apparent difficulties in trying to use mathematics to understand these kind of questions. Firstly, there's a lack of principles. So in physics, for example, in many other areas, you might find widely accepted principles. And these principles are usually expressed in terms of mathematical formulas, like Newton's law of gravity. But in biological and ecological problems, most of the time, there's no such principle at all. And secondly, and for these kind of problems, so even to get experiments done is impossible very often. it's very, very difficult to get field data because you need a long time, and also it's very difficult to get any useful data. And due to these difficulties, of course, there have been debate between theoretical researchers and field biologists. So on how mathematics can be useful with the mathematical models can really give you some meaningful result. Well, nevertheless, so the mathematical modeling has been going on and achieving many successes. So there's a book, a bit old now, but the Princeton Guide to Ecology. They have a list of many success stories. The first has to be, well, in that book, is this logistic model, and used widely to describe the fluctuation of a population. So this is a simple model looking like that, where these U represent the total population at a certain time t. And then when t changes, you want to know how the population changed. It turns out that this differential equation proposed by Verhulst was very useful. And it tells you that, so this constant k, there are two constants, a represent the growth rate, and k represent the carrying capacity, how much population the environment can support. And this equation tells us that if we start with a bigger population than the carrying capacity, the population will decrease with the time, eventually goes to the carrying capacity. If you start your population with a lower number than the carrying capacity, then the population will increase in time. So this turns out to be rather useful, has been accepted by many biologists. So that's one of the success stories. And there are also other models, models involving more than one species. And these Laureate competition model, usually involving two populations. And they have been used to demonstrate competitive exclusion. So if you have two similar species living in the same environment, usually one of the species will disappear. So this extinction, exclusion, competitive exclusion. And there's also this Leslie matrix model. And I know you see in one of our first year classes, first year unit. So used to describe how population changes with generation after generation. And there's also this Hollins functional response. There's a further development of the Laureate model, replace some of the function there by this one, and which turns out to be more useful and has been widely accepted. And there's also this famous model by Anderson and May on infectious disease spreading. And their models were so successful that many governments base their decisions on immunization on these models. And by the way, so Robert May, perhaps many of us know, it's a Sydney boy, was a Sydney boy, and got his first degree in University of Sydney, and then moved overseas, and then moved back and eventually moved overseas. So he retired from the president of the Royal Society in the UK. And unfortunately, he passed away during the COVID period. Now I have to mention that, so the mathematical models involved in the examples I mentioned are what we call ordinary differential equations, and they already appear in our undergraduate university courses. For modeling of a propagation by definition, and investigate how species evolve or move in the environment. So a differential equation involving only functions of time is not enough. So we have to involve space. So we usually use t to represent the time variable, and x for the space variable. And then things become more involved. So we have to use what we call partial differential equations involving partial derivatives, because we have multivariable functions for time t and space location x. And one kind of partial differential equations which have found many applications in propagation phenomena as well as in chemical reactions. Actually, this name, reaction diffusion equations, originates from their application to chemical reaction problems. And they describe the change of a density function, which is a function of time and space location x, and involving a reaction term that takes care of substances transformed to each other. There's also a diffusion term in these equations, which takes care of the spread movement of, say, molecules of the material, of the substance. Now, so these equations originally used to describe chemical reaction turns out to be also very useful for processes of a non-chemical nature, and which is what I'll talk about mainly tonight: ecological invasion, spread of epidemics, tumor growth, wound healing, and pattern formation of animal coats, and so on. Well, what does a reaction diffusion look like? Well, looks like that. That's the one appearing on the first slide of my talk. Now I'll start with some successful stories using reaction diffusion equations for propagation. So these start with two papers appeared in 1937, simultaneous, in the same year, but independently. And one is by Fisher, and the other is by what we call KPP, standing for three former Soviet Union mathematicians: Kolmogorov, Petrovsky, and Piskunov. So Fisher's paper just used these reaction diffusion equation, and here that's the diffusion term. And if you assume individuals in the species move in space randomly, like doing a random walk, like molecules in the air move randomly, and then you would derive this term. And this red term represent natural growth, and in reaction diffusion equation, this is called the reaction term. Now, for population problems, we call this the growth function. And U is the unknown function. It stands for the density of the population carrying a certain good gene. So Fisher and both Fisher and KPP, they were interested in how a good gene spread in the population. So this U now stand for the density of population carrying that particular gene. And there are two parameters. Capital D stand for the diffusion rate. A bigger D means individuals move more frequently. And A stand for the growth rate. A greater A means so they reproduce faster. And that's KPP, Kolmogorov, Petrovsky, and Piskunov. They used a similar differential equation. So what they used here is not this particular function of a U, and they use a more abstract one, but they assume that abstract function behaves like this particular one used by Fisher. And both Fisher and KPP discovered that, so these equations have a certain kind of special solution. There are infinitely many special solutions, but they singled out this one. They call, well, now we call traveling wave solutions. And Fisher actually has a different name for it, but people forgot about his name, and everybody remembered this as traveling wave solution. That is because the solution looks like a traveling wave. For a fixed time, the solution as a function of a space variable x gives you a curve like that. And when time change increases, the curve doesn't change its shape, but shift to the right. And this is just like a wave, a traveling wave, moving to the right. And there's a speed here. C is a constant, is the speed. So they found these equations have these kind of special solutions. It turns out that these special solutions determine the long-term dynamics of these propagation phenomena. And in particular, they believed that, so there's a C0 given by just these two parameters in the equation, A, growth rate, and capital D, the diffusion rate. So these determine this number C0 for speed greater than or equal to this speed. You definitely can find such a traveling wave moving with the speed C. And these smaller, well, for speed less than these C0, you don't have such solutions. So, and then they believe this C0 would be the speed they are interested in. That is, the gene spreading the population with the speed C0. And Fisher couldn't prove it to the level mathematicians would agree you did prove it. So mathematicians would argue, no, you just indicated, you speculated. But KPP did provide something rather rigorous, though not general enough. They showed that, well, if the initial population is like that, so for x less than 0 in one space dimension, it equals the carrying capacity 1. To the right is 0. There's no such population. If you start with such a distribution of a population, then when time increases, the solution curve would convert to such a traveling wave. And because of that, they believe this C0 is the spreading speed of the good gene in the population, in the environment. Of course, we can argue this model is too simple, and it's not based on first principles, and it's oversimplified. So how they assume the available space is an infinite straight line. But we don't get this in real life. And also they assume individuals in the population moves in space randomly, like a molecule in the air. Well, if you talk about a human population, they move more in more complicated patterns. And they assume the environment is homogeneous. It doesn't change with time, doesn't change with location. Whenever you look at the environment, wherever you look at it, it's the same. And the thing is that to achieve these mathematical conclusions, well, you really have to use this oversimplification. If you don't do it, it's too complicated. The mathematics, at least at that time, couldn't handle it. Then how could you make me believe what you obtained? You say there's a spreading speed. It's reliable. It's correct. So for over several decades, I would say, they have not been widely accepted. And even mathematicians, most mathematicians don't know their results. But the fate of the model was about to change in 1951. So we come to this masquerade again. In 1951, there's a paper by Scanlon, which really made a difference. So he looked at the spreading of this animal. That was 1951. The spreading happened during this period, so several decades before. And this spreading was documented in a book, appeared in 1930. That was even before 37, when Fisher and KPP did their modeling. But what Scanlon did was he looked at a diagram in that book, appeared in 1930. So this diagram actually is a documentation of the spreading of the masquerade. We can say there are many closed curves, not regular, because the environment, there are mountains, there are rivers. So each closed curve includes the area of the population range at a particular year. So they followed these for over 2 decades. So each of these closed curve was obtained in a particular year. And actually, the curve represents the spreading front, the range boundary of the species at a particular year. And you can see they expand over the years and started near Prague. And then eventually they spread, within 2 decades, they spread almost everywhere to the European continent. But what Scanlon did was he just used this diagram, tried to measure the area of each of these enclosed by each of these closed curves. Of course, each closed curve corresponds to a year, so the area changed with the time t. And he took the square root of that area and plotted this number against different times. And that's what he obtained. So these points, square root of the area, increases with the time, but in a linear fashion. Yeah, that's really interesting. Out of these graphs, no one would believe it has anything to do with the mathematics. Now there's a mathematics, right? You cannot deny it. There must be something behind. So you estimate the area, took the square root increase with the time linearly. Well, why took the square root? That was because in ecology, there's a notion called the range radius. So the population range gives you an area, but if you look at a disk with the same area, but a radius r, well, that's the relationship, yeah? A disk with the radius r has the area pi r squared. So if you let these two equal, you get RT equals the square root of these divided by square root of pi. A universal constant square root of pi over 1 times these square root of the area. Now that's the range radius. So basically the range radius is a rough average of the range boundary to the original spreading place. So this is an average distance of how far the animals has been run away from the original spreading place. So this has been used widely by biologists and ecologists. So Scanlon took the square root in order to get the idea how the range radius increase with the time. Well, his observation is they increase linearly. Now, if you say linearly, then this range radius over time proves a constant. That's what we usually the spreading speed. Well, by that time, we recall that was exactly what the Fisher-Kappa model claimed. They claimed the spreading of a species has a speed, C0. They even have a formula for that. You see, that's the formula. If you know the growth rate A, if you know the diffusion rate capital D, well, that's the formula, very simple formula to find this spreading speed. But of course, at the beginning, perhaps no one believed their story. But after this example, people come back to look at them much more seriously. Moreover, well, let me just pause to look at the story of Scanlon. He was a statistician and ecologist. And I failed to find a picture, a photo of him. So this is the Wikipedia entry for Scanlon. And that's the paper I mentioned, 1951. Now, furthermore, after what Scanlon discovered, people looked around and they found other stories spreading of Himalayan thaw in New Zealand. There were field data. You do the same thing, estimate the population range area, took the square root and see how it changes with the time. You get a similar story. Yeah, the range radius increases with the time almost linearly. And spreading for birds. So European starling in North America, similar story. And house finch, similar story. And Japanese beetle in North America, similar story. So there are many evidences supporting the claim that species spread with a spreading speed. And then people, there are, these are much later works. They look at many different species. And of course, there are ways to find the diffusion rate. There are ways to find the growth rate. Once you get these two numbers, remember there's a simple formula, 2 square root AD to give you the spreading speed. That's the theoretical one. These are the observed ones. So now we can already realize the difficulty with the mathematical modeling of ecological questions. Even for field data, you don't get one particular value for the growth rate or for the diffusion rate. You only get a range. And this is the theoretical one. These are the observations. Most of them are rather good match, except the second one. For the second one, no, the third one. Yeah, the third one is the one I really don't know what's the animal. then I checked it's what we call cereal leaf beetle, is this guy. So they spread much faster than the theoretical rate. Or I was guessing maybe they spread faster because long distance dispersal. We'll come back to that later. If there's a long distance dispersal, usually their spreading rate is much faster than these theoretical ones. So these beetles could be carried by people, by car, or by train to far away place instead of they fly around. Now, coming back to the theory started by Fisher and KPP. And in 1978, these two mathematicians from the University of Minnesota, I actually met Weinberg in 2012 when I visited the University of Minnesota. We had some discussions about spreading. And they had this classical paper appeared in 1978. They really gave the theory a much clearer meaning. And their results are much more convincing than the earlier ones by Fisher and KPP. So they looked at the high dimension version of the same model used by Fisher and KPP, and they proved rigorously this result. And this result basically says that, so the population range is roughly this ball with the radius is approximately C0 times t. So the radius increases linearly with the time, but with the rate C0. C0 is the one Fisher and KPP claim that's the spreading speed of the good gene in the population. So they now proved this result, which is more convincing, because if you look at, well, I have to use mathematics. Basically, it means, so for a time t fixed, you want to understand what's the population range. Well, you might say, if the population density is greater than a certain number b, constant b, then I say all these places where you have such density, you would say that consists of a population range. And then you do the same thing as what Scanlon did. You took the square root and so on. And then you found the range radius. And then this result really tells you, if you do some analysis, it tells you, indeed, this range radius of this population range increase with this rate, C0, and which is calculated by these 2 square root AD. And this rate, you might say, well, how about I change this b? Well, this rate doesn't change with b, though this set changes with b. Now, of course, so there's a shortcoming with this model. The shortcoming is the following. And you could ask me why you choose b greater than 0 and look at the density greater than b. Why not 0? The natural thing, to look at the population range, is where the population density is positive, right? It's not greater than some constant b. But if you use this as the population range, then you are in trouble. The population range, though at time 0, you assume the population is locally concentrated. That is, the population range at time t equals 0 is a bounded set, like it's Armidale. It's not the entire New South Wales, not the entire Australia. But if you use this model, it tells you once t time is positive, the population range immediately becomes, well, here the entire Euclidean space, and we could say that's the entire universe. No way, that's not right, right? But how do we overcome this? Especially, sometimes we are very, very sensitive about what's the population range. Like if the species is the COVID virus, we really want to know where's the boundary, right? You cannot say initially it's started from Wuhan in China. Now the next moment, so the population range is entire universe. No. But there's a way to overcome this difficulty. That was what I did with my collaborator, Professor Zhigui Lin from Yangzhou University in China. So 2010, we tried to modify the classical model and assuming this differential equation is not satisfied in the entire universe. We just say it's satisfied over the population range. So we start with the one-space dimension. And we assume that the population at the range boundary has density 0. Outside the range boundary, of course, there's no population. And then to make the problem well posed in mathematics, we have to add extra equations to govern the evolution of the range boundary. So these are extra difficulties. And there are also extra reasons for people to argue with you because you don't have a first principle. How do you know these are the right equations to govern the change of the range boundary? And well, we did find biological assumptions which leads to these equations, and the biological assumptions are reasonable. And also we looked at how the population change under these modified models. So we found that if you look at the population range, you look at the population density, so there are two possibilities. Either the population vanishes in the long run. So as time goes to infinity, the population range would just convert to a finite set. So in one space dimension, we say it's a finite interval. And the density function converts to 0. So the population disappears. Or the population range converts to the entire real line. So we assume the universe is one space dimension. And the density function converts to the carrying capacity. We normalize the parameters so that the carrying capacity is 1. So there are only two possibilities, either vanishing or spreading. And we also find sharp conditions to govern exactly when this happens, when that happens. But these are mathematical conditions. I won't say what exactly it is, except saying if the initial population is small, it will vanish eventually. If the population is large enough, and it will spread successfully. And also, we talked about the spreading speed, right? Discovered by the model of Fisher and KPP and supported by many real-world evidence. And for the modified model, we still have a finite spreading speed. So we retained the good features of the old model. But we do have, the model does give us a clear population range. So we don't have to introduce some parameter B to say, so density greater than B gives you the population range. So here the model gives us the population range by itself, clearly. Now, what's the relationship between the new model and the old model? Well, even mathematically, they are connected. So remember, in this model, we introduced a parameter mu here. So I didn't, don't think, did I? Yes. So the mu has a biological meaning that is 1 over mu is proportional to the sacrifice of the population that is made near the range boundary in order to expand its territory. So the population has to make some sacrifice. How big is the sacrifice? Well, it's proportional to 1 over mu. The bigger the mu, the less the sacrifice. Well, mathematically, we proved that when mu converts to infinity, or the sacrifice 1 over mu converts to 0, we recover the classical Fisher KPP model. So that's the relation. In other words, if you assume the population doesn't have to make any sacrifice in order to expand their territory, then you get the classical model. And of course, there are, for both the classical model and for the model with a changing boundary, there are many extensions to cases where your growth function is more general, like this one, to include alley effect. Alley effect says that there's a threshold density determined by the environment and also by the species, that if the population density is below this threshold, then it suffers. The growth would be negative. Above it, then the growth would be positive. And also extension to high space dimensions. I mentioned these Aronson Weinberger work extending Fisher KPP to high space dimension. But for the moving boundary model, there are also extensions to high dimensions and also to heterogeneous environment. For example, time periodic environment. This is a very reasonable because so all the species live in our environment subject to daily change of temperature and other things, and also seasonal change. So it's very reasonable to assume the environment changes periodically in time. For these simple cases, there are already extensions of the basic theory to these more general situations. And also shifting environment to include factors for climate change. Climate becomes warmer, but it moves, the climate changes gradually, but perhaps with the speed, like a spreading speed. So this has been taken care of. And another thing is to change the assumption about movement, dispersal strategy of the species. And in the earlier models of Fisher KPP and our extensions, we always assume the individuals in the species move in space randomly, like doing a random walk. But in practice, they are more complicated. In particular, there are more and more attention paid to situations where long distance dispersal is involved. As I just mentioned, for this little bug whose observed spread speed is much faster than the theoretical one. Maybe that was because long distance dispersal. So apart from their flying around, they might be carried by human being or by people driving the car to far away places. So that helps them enhance their spreading. And also these moving boundary equations, there are many different ways to describe them, and there are variations. And now there are more and more work taking care of all these kind of situations. And one particular assumption is to assume that the range boundary moves forward or backward depending on the population chooses a preferred population density. And these would change the mathematics rather significantly. And this actually is a part of the my Laureate fellowship project. There are other things, but this is one of those. So now I just want to show some numerical simulation obtained from from our models. This is a simulation of the new model with a moving boundary, but in two space dimension. And suppose we start with a population range like an annulus with a cot. And we want to know, we know the theory tells us, well, the population range, because you assume the environment is homogeneous. The theory says the population range will evolve into a big disk with the radius increasing linearly in time. And our simulation indeed says that's the case. So these red color means higher density, blue means lower density. You can see it's getting rounder and rounder. If you keep your simulation going, and you will see the population range would increase linearly. And that's another simulation. You can see, so these two connected ranges would get connected, and eventually they want to form a big disk with increasing radius. But to do this simulation is very time consuming. For each of these, you need like over 10 hours. And this is for one space dimension. It's much easier. And you need a few seconds to finish one simulation. So in two space dimension, it's much more costly with the simulation. So this is a case where, remember I mentioned that Fisher KPP discovered that. So these are very special kind of solutions we call traveling wave, determine the long-term dynamics of the model. And these are two examples. You start with, say, a population looking like this. And then you let this as the initial population distribution, and then you want to know with the time increase, how does the population density look like? How is the population distribution? And you can see very soon they form these traveling waves, you see, and with the front moving with a linear speed. That's the speed C0. And the second one is a case that, well, so that's homogeneous environment. How about time periodic environment? So that's what happens. If you time periodic, still you have the same feature of a traveling wave, though because of environment change, these wave like shakes. There's a periodic perturbation, but still it's like a traveling wave. So this basic feature is retained. And finally, I want to mention my collaborators. And there's an entry for myself in this MathSciNet. Previously, it's called Mathematical Reviews. It's a publication by the American Mathematical Society. At the university library, we still have many hard copies of these. But nowadays, most people just look at the internet. And everybody, if you publish in mathematics, you get an entry, you get an ID number. It tells many things. So now I just want to concentrate on my co-authors. And I have quite a few. And the bigger the size of the name here means more joint publications. And these Norman Dancer was my postdoc supervisor here at the UNE. He left in 1993, 2 years after I arrived. He moved to university and then he retired some years ago. And Zhou Mingguo I was Nomenden's first postdoc fellow. He was the second, arrived a year later. But after he finished the postdoc, he went back to China, but we kept doing joint research. We had many joint publications. And Wen Jianyi is here. He's my colleague, has been doing a postdoc on the ARC discovery supports. Ray Peng was one of my former PhD students. We still keep collaborating. And Maolin Zhou was a former postdoc. He was here for 5-6 years. He's now a research professor in Nankai University in the Chen Institute. And there are many others. Rong Wang was one of my recent PhD students who finished a couple of years ago. We have a Kang. Yes, he finished also a couple of years ago. And we have a team, and he was helping with the numerical simulation and co-supervising several PhD students. And by the way, the last 2 simulations was done by Nagas, who is here. She is my current PhD student. We are waiting to have a joint publication, but we will get one soon. I think that's all. Thank you.
Thank you, Yihong. That was fantastic. We've got time for questions if anyone has a question. I might just check if there's any online. Do you mind opening the chat? There's something in the chat. I might, yeah, do you want to ask a question? Got a microphone here. I've got a wandering mic for those in the room.
Okay, thank you very much, Professor. Really interesting. So I come here because of the I'm a PhD student in Agbu. So we are trying to model, pretty much we are trying to model the phenotypes in generations over generations. And I'm also a friend of Nargis. We're both running around. So when I saw a video on university's Twitter account, I found that there's a very close relationship between this methodology and what plant breeding and animal breeding does. And actually, I was really shocked to see R.A. Fisher was the person who invented the field of quantitative genetics, which is now very much used. It's the foundation of breeding. My question is there any validity or any methods to predict the spread or predict the outcome? I mean, extrapulation. And is it a valid thing, or is there any evidence that prediction is also works based on this?
Yeah, I don't know any. Part of the reason is because, so my work is just trying to get some basic mathematical result that can apply to many situations. Of course, if it applies to many situations, it won't be sharp. So maybe it tells you the principle, saying perhaps it's predictable. However, if you have a specific question, specific species, and the usual way to do things is you modify the oversimplified basic model to suit your situation. But the for the oversimplified basic model, there are some mathematical theory or predictions. They may or may not be right for your specific one, but you can use that as a kind of a guide to just create a more specific model suitable for your particular situation. And then usually you could just run nowadays numerical simulation. The computers are rather powerful. You don't have to wait for someone doing theory to prove it. You can just run it to say whether you have the phenomenon you are looking for.
We've got one question from Susan. Does your model fit the pattern of spread of cane toads in Australia?
We haven't tried. I did try to try to find to discuss with Rick Shine, the hero of
cane toads.
Research on cane toads at the university, but I haven't managed to do that yet. And just as what I said a moment ago, so if you really want to model the cane toads spreading, you have to, again, perhaps I would be very happy if the basic oversimplified model gives you a good start point and to modify it to suit your situation. And for example, for the spread of a cane toad, it's spread over all Australia. But the Australian, this continent is very varied. There are deserts, there are rivers, mountains, and so on. So to anything accurate with a certain kind of accuracy, you have to build into all these heterogeneous environments into your model in order to get a reasonable prediction. And the model I talked about usually assume the environment is homogeneous. That's why you see the simulation tells you in two space dimensions, the population range become more and more round. It's because you assume everything is, everything is everywhere, things are the same. So perhaps you can have that in an experiment, but in the real world, no way. So you have to build your specific situation, the change into the model. You modify it, then simulate. Then I would believe you would get something reasonable. Yeah.
I wonder, during COVID, we saw probably at the end of the first year, we saw waves of different varieties of COVID. So we would see the Omega coming, and then, oh no, there's Omicron, and that would sort of take over Omicron, and Omicron would, Omega would go away and Omicron would take over. Does your model have you used it to look at where you have kind of competing populations?
No, at least for me, I felt our model are too simple because the spread of COVID are mainly caused by human being. How human beings move around is just beyond these random diffusion or even the ones long distance dispersal. We could only theoretically locate some nice looking kind of kernel functions or distributions. These are too simplified. I don't believe these kind of models can give you accurate predictions for things as complicated as spreading for COVID. So many different kind of viruses, and also people moving around in such complicated ways. And also the government introduced lockdown, all these policies change all the time. So these are too simple for that. Perhaps if you try to look at a spreading of a virus by some animals, like even mosquitoes, that might be closer to your assumption. But for COVID, these are too simple. Yeah.
Can I just check if there are any other questions? I might just, it's a bit, I don't know whether this is, well, I'll just ask it. So we saw at the beginning of your presentation that the kind of concept of this movement came out of chemistry. So it went from chemistry into population. Do you see that this type of mathematics could move into a completely different domain as well?
Yeah. Now, for example, there are people using these to model the spreading of rumors or information. Yeah, that's why actually I'm also trying to modify these models to try to have some use of how information rumors spread. And then instead of this Euclidean space, people usually try to replace these by networks. And I had a paper on that, but that was a very simple one to say, you look at the environment is in the river. The river have branches and so on. These are a very simple, in mathematics, we call these spreading over graphs. Graph is a special kind of networks. So like a spreading of a COVID, you could have these big cities, centers as a point. And these connections by these edges, this would be a graph. And for spreading of rumors, you could think of, so everyone has a mobile phone, that's a point. If any two people, they have a connection, then there's an edge connecting them. And then, of course, this could be a very complicated network. But there's a possibility. There are already people applying these kind of Ricci diffusion equation over these oversimplified networks. But these can be, you can refine your model, make it more realistic, and then the theory is not helpful anymore, but you can do simulation. Now, that's a good thing is once you have a good direction based on some oversimplified mathematical theories, mathematical models, maybe that can guide you to build more realistic models. And then simulation can help you really check whether your model works or not.
I guess in that case where you're looking at spreading of rumors change over time. So you imagine that as they change, they become dynamic, more and more, crazy or controversial, and they spread even further. So have you done any modeling that's kind of looked at how the vector changes?
No, not yet, but that's also part of one of the topics I want to look at
for the
in the Laureate.
Yeah.
So I want to look at how some of these theories can be extended to the case where instead of a Euclidean space, one space dimension, n space, but replace them with networks. In mathematics, we call graphs. We can start with the simple ones, and once with the simple ones, that I hope you can get a deep mathematical theory, and then you can get help with the simulation.
Can I check if anyone else has any questions? Any from the mathematicians in the room? Don't be scared. I might just ask one final question then. So what, at the end of the Laureate Fellowship, that's a 5-year period, what are you hoping, what are the things that you're hoping to deliver or complete or discover over that period?
I think perhaps my biggest hope is a 5-year period, many young people will be involved. I hope by the end, some of the young people would become research leaders to continue in various directions and to do things better than me.
That's a great vision. That's a great outcome too. And let's hope that you have all the success in reaching that. So I'd like everyone to join me in thanking Professor Yihong Du. And thank you so much for such an interesting presentation.